Hi there, everybody, and thank you and welcome to the Tony's Tech Talks this afternoon. And these Tech Talks are organised monthly, and one of the challenges, I guess, for me as the presenter in these Tech Talks is that I don't know in advance what the subject will be, what subject will be chosen for the actual Tech Talk, although I am told that particular day, which gives me a couple of hours to prepare, which is obviously great. So today, anyway, the topic of du jour, so to speak, and the one that has received most votes is the Kantan Neural feature of our new platform. This is a new feature that we've developed that allows you to build both statistical engines and neural engines. And when you combine that with KantanLQR, Language Quality Review, that's our language quality review platform that's built into the Kantan platform, you can now do comparisons between SMT output and neural MT output, which is pretty cool. So what I'm going to talk about today, guys, and firstly, thank you very much for suggesting that we talk about neural. It's always it's a hot topic in our development team, particularly in our Kantan Labs team. And what I'm going to talk about today is an experiment that we ran, and we've just recently complete. We ran it over the last 2 to 3 months, where we actually compared the output of SMT engines to neural MT engines to see what we would find. And the results we got, I have to say, well, they weren't unexpected, but we were startled by the results that we got. So I'm going to share those results with you today. And these results are also part of a rather large and complicated white paper that we've produced for some of the MT conferences that we're going to attend later on this year. So I am recording this presentation, so if you want a video of this presentation later on, feel free to request it. It will be published in the usual location on our website. Okay, so what are we going to cover today, guys? Well, the first thing I'm going to cover is what's the scientific rigor that we used in setting up the experiment to compare SMT to phrase-based statistical MT systems. Well, the first thing we did was, you know, I've read an awful lot of papers on this subject comparing neural MT output to SMT output, but very few of the papers have developed systems based on the identical same training data. In other words, they're trying to compare two dissimilar systems, so it's like comparing apples to oranges, okay? But the fact that the systems are not even identical really, in a lot of ways, invalidates the results of those SMT or those results of SMT against NMT. So what we decided to do this time was change the rules. Wouldn't it be really cool if we used identical training data sets, identical test reference sets, and we built an NMT, a neural MT system, and then we also built the equivalent SMT system. So now we have two systems identical in their training data, only differing in their method in which we're doing the data modeling or deep learning. In addition to that, we also made sure that we're using exactly the same test reference sets. And the reason we wanted to make sure that they were the same test reference sets for the neural MT as well as our statistical MT is because we were going to use F-measure, TER, and BLUE automated scores in order to determine if the engines were going to produce, you know, likely produce good results and so on. So we have some kind of normalization of automated scores. We're using exactly the same test reference set to actually test the engines, be it a neural engine or a statistical engine. In addition to that, we set up a team, 5 teams in fact, of native speakers, professional translators, and the minimum size of a team was 3 professional translators. So we ended up with a minimum of 15 translators doing the actual evaluation of the translation. And we used KantanLQR, our platform for language quality review. It's available free to everybody that subscribes to the Kantan MT platform, and we use that to do A/B testing. And we asked a simple question: is neural output for this particular source segment better than the statistical output, or is it the same? So we asked them those questions, and then we tabulated our results. So here's the training corpora that we use. So you can see there we chose 5 languages. We chose English, German. The reason we chose English, German is because German is a complex, morphologically rich language. We have a lot of distortion in that language during the decoding or the translation process. The verbs tend to move to the end. We've got compounding and things like that. So there's a lot of challenges there. We then chose English to Chinese, another very challenging language. English to Japanese, very, very challenging language. And then we did Italian and Spanish as well. Those last two languages are probably languages that you would expect SMT engines to perform very well. So it'd be interesting to see how NMT, neural MT engines performed. You can see the amount of parallel sentences we use. These are by no means small engines, ranging from 44 million words all the way up to 110 million words. That's what the TWC, the total word count column is, and the UWC is the unique word count. So that's the unique word count in those engines, just to give you a sense of how deep those engines go in terms of unique words for a particular language arc, a language arc being English, German, a language arc being English and Chinese and so on. You can see that we've got a lot of unique words there, which means that these engines, although we've trained them on the legal and medical domain, they probably could be used in an open domain scenario and do reasonably well as well. So now that we've normalized the training data, and it's the same data used across both engine types, what's the training time like? Well, for SMT, as you know, if you're familiar with using the KantanMT platform, the SMT training time is super, super quick. So, for instance, for the German engine, it took 18 hours to train that engine. It took 6 hours to train the Chinese engine, 9 hours for the Japanese engine, and so on. So that's all within a working day, and that's what we refer to as production capability or production viability. In other words, if you have an engine that takes 2 weeks to train, you're not really going to be able to use that in a production environment. It just takes too long to train it. You know, the project's finished by the time you've got the engine customized. So SMT is super, super fast, but look at the training times on NMT. You can see that while we've speeded up the training time for NMT substantially, we're still not where we want to be. So there's some work left for us there. Look at the training time for the German engine, our biggest engine there, 110 million words. And by the way, that's 110 million source words. So, you know, add in the target words there, you're talking about 250 million words of training data. And you can see that took 92 hours. So, you know, our target in development here is to reduce the training time of a neural engine to be less than a 24-hour period, and that's what we would define as being production viable. In other words, you can do that within a working day, and the next day you can start using that engine. So we have a little ways to go there, but we're certainly going in the right direction. When we started looking at neural MT, God, about 9 months ago now, maybe close to a year ago, you know, an engine was taking 3 to 4 weeks to train. So we've really been able to compress that in substantially, but we're not quite. Our standards are forcing us and compelling us and motivating us to make it even faster again, and I'm sure we'll solve that problem later on this year. Then let's look at the automated scores then. So in the blue columns we have the SMT, the phrase-based statistical machine translation. So we've got the F-measure scores, the blue scores, and the TER scores. And then in the green columns we have the equivalent automated scores. Remember, we're using exactly the same test reference set across both engine types here. So we've calculated the equivalent scores from the output of an NMT engine. And you can see there that there's some kind of interesting insights here. Now, I know this is a massive figures on the screen, but let's graph it because we can see the trends in the graph a lot easier. So what I'm going to do here is I'm just going to show you what this looks like if we graph it. So let's just graph the actual columns there, and you can see there at the bottom of the screen we've just shifted the table up a bit, and at the bottom now we've drawn these nice little graphs, and each of those bars is depicting the various different scores, F-measure, blue, and TER score, right? Now what's interesting here, guys, and the first insight into this experiment was, let's get rid of F-measure and TER scores, right? So let's just fade them out of our data set, okay? So what we're left with is blue scores for in the blue column, which is for SMT blue, and in the orange column there, or the burnt red column, we have the blue scores for neural MT engines. And the interesting insight here is, guys, that in all cases we have never been able to build an NMT engine that has a higher blue score than the equivalent SMT engine. Now, that goes against the grain of nearly every academic paper I've read comparing NMT to SMT. It's quite incredible that most papers tell us that they have better BLEU scores. In our experiment, where we're dealing with identical training sets, identical reference sets, we have not been able to achieve that. And you can see how many hours we spend training these engines. So that's the first insight. Okay, so we can't exceed the BLEU scores. Now, let's now see if that is significant when we ask a translator to choose what the best translation is. Is it an SMT translation, or is it a neural generated machine translation? So to do that, we set up an A/B test, an A/B sampling test. We used 3 translators across all 5 languages, so we had 15 professional translators. We used the KantanLQR platform to do this, and as you know, the KantanLQR platform, it's built into Kantan. It's a really cool feature. It allows you to run language quality review projects. Now, one of the projects is a A/B test, and you can actually have AB, ABC, or ABCD tests. You can do more than 2 data samples, but you can also do language quality review using the DFQ dynamic quality framework, or even the MQM framework. Those testing frameworks are built into this application. So what we did was we set up an A/B testing application, and we asked the translators to basically make a very simple decision. We displayed the source text at the top of the screen. We displayed then the output from the SMT or the NMT engine beneath each other, and we asked them to select the better button or the same button. So we're actually asking them to effectively rank the translation from that. Now, one of the really cool features of KantanLQR is that it's real time. We can track who's working on the project, how many people are working on the project, where the project is, right down to the second, because it's all real time. Stats come up through on your dashboard. And eventually we ended up with this one graph that tells us what was chosen as the same for the translator. In other words, the neural MT was identical or equivalent to the statistical MT, or that's sample A was better than sample B. And of course, we randomized those samples, so at no time was there a bias in the decisions made by the translators. We randomized whether SMT was displayed as the first translation suggestion or the second, and so on. So they could never figure out, or they could never predict what was SMT or NMT. So what were the results that we got? Well, interesting enough, here's the results that we got in terms of ranking. Okay, so what I'm going to show you here first is a graph that tells me of the 200 segments that we evaluated, which is quite a good, decent size sample that has to be said, across all 5 languages, by the way. So each language had a unique set of 200 segments. In English Chinese, 37% of the translation was deemed by professional translators to be the same or equivalent. 21% in Japanese, 13% in English German, 24% in Italian, and 10% in Spanish. Okay, the average across all languages was 21%. So 21% on average was viewed of being the same or equivalent or identical. Okay, so what's the other 80%? Well, if we superimpose then the segments that were deemed or ranked higher than NMT, in other words, they came from the statistical engine, you can see those blue graphs there. So 24% of the segments, 1 in 4 segments in the English Chinese LQR or A/B test was rated as being better in the SMT. Okay, you can see in the English Spanish it was 28%, slightly higher. Okay, and on average 25% was the average score across all 3 engines. Now look at this, guys. Here's an interesting insight. Now if I superimpose over that the output of neural, look at the difference neural has made. So these are identical engines, identical reference sets, only differing in the techniques we've used to build the engines. So this is the first time we've been able to compare apples and apples, or like engines, only difference on SMT or NMT. And you can see the results are startling. 37% of the segments are chosen from English Chinese, better in NMT. Look at Japanese, 58% of the text is viewed as better from the neural engine. Pretty staggering. 53% in Germany, 56% in Spanish, even those languages that we'd expect SMT engines to do well. When you have an identical engine, neural has beaten it hands down, and that's pretty insightful and pretty staggering, actually. We didn't expect the difference in the results to be so different. So what conclusions can we draw from that? Well, let's just recap on the type of test we did here. So the first thing we did was we created identical phrase-based SMT systems and neural-based MT systems. We used a commercial setting, so in other words, we didn't want to leave these things training for weeks and weeks and weeks. We wanted to train them in a relatively short period of time so we could actually get them into production quickly. We use identical training scenarios, identical training data sets, exactly the same, word for word, segment by segment in terms of test reference set. We created the same automated scores across all engines to get comparative scores between SMT and NMT. And then we conducted human-based A/B sampling tests. Okay, so there's the kind of rigor behind the test, just to summarize that. So in terms of translation, the conclusion that we can draw is that determined by native speakers, speaking professional translators, in all cases, neural MT ranked higher than SMT. In fact, in a lot of cases, substantially higher. And we observed that of the low scoring, if you looked at the blue scores for individual segments for neural engines, they were low scoring blue segments coming from neural MT. 48% of those were selected as being better than the equivalent SMT engine output. So even in low blue score scenarios, we were still half of what the engine was producing was selected as better than SMT output. And that really gives us the conclusion that blue is susceptible to underestimating the quality of NMT engine. In other words, it really isn't of any utilitarian use if you're comparing the like-on-like output of SMT versus NMT. And I think we've kind of realized that or predicted that in the industry, but now we have a test that really conclusively proves that. If you use identical engines, neural engines will always outperform statistical engines. So thank you very much, guys. I'm delighted we were able to present these results to you, because it's taken us 2 to 3 months to run these tests and analyze the results and collate all the data and so on and so forth, and organize the translation teams and so on and so forth. And you can see, hopefully, that neural MT is a technology that we're going to have to really embrace. It's a technology that we're going to have to really look at ways to get it into production quicker than it's working today. And it is a technology that has the potential to redefine the quality for machine translation in the industry today. And one of the really cool things that you can do today on the Kantan platform is you can have the best of both worlds. You can have statistical-based systems as well as neural-based systems, and do those experiments yourself to make sure that you feel confident that your neural systems will outperform your existing statistical-based systems. Well, thank you very much for your attention today. I hope this was helpful. I hope it was insightful and meaningful, and I do look forward to talking to you again at Tony's next Tech Talk, which will be in 3 to 4 weeks' time. Thank you very much, guys.